Hello everyone, welcome to our third lecture on gravitation, and in this lecture we are going to discuss about free fall. So what is free fall? You drop an object and only force acting on that object is gravitational force of earth, then object is said to be freely falling object. Suppose I am dropping this marker and this falls down, this marker falls down. The only force acting on that marker is gravitational force of earth, and that we call gravity, and no other force is working on that marker, so this marker is said to be freely falling object. Now if I drop this, I throw this marker vertically down like this, so I am applying some force on this marker, then this marker is not said to be freely falling object, because one force acting on it is gravitational force of earth and other force created by my muscles, and that's why it is not freely falling object. Now when you drop an object, its initial velocity is 0, and as it go down its velocity increases. If initial velocity is 0 and its velocity is increasing, then we can say this object is undergoing some acceleration, and that acceleration, in case of gravitational force of earth, that acceleration is called acceleration due to gravity, and we represent that with small g. Now if you drop a paper, and a stone, both these objects will reach the ground at same time or at different time. Obviously stone will reach the ground before that paper, so can we conclude that a heavier object reach the ground first, or heavier object undergoing more acceleration? No, this is not the case. But then why this heavier object like stone is reaching the ground first? So here, when you drop something, air resistance work on these objects, and this air resistance depends on the density and surface area of the object. If object is heavier, means more mass is concentrated in less area, then air resistance on that object will be negligible. And if object is lighter, and we can say less mass is concentrated in very huge area, then air resistance will be very high. Like in paper, if you take a paper, then for 1 kg mass you have to take too much surface area, and for a stone, if you take that much stone, its mass can be 1 kg. So paper is very light object, that's why more air resistance is working on that, that's why it is falling slowly. Now air resistance depends on mass of the object, or we can say density of the object, and that's why paper falls slowly and stone falls faster. And this g, acceleration due to gravity, is independent of the mass of the object, means everybody must reach the ground. If you are dropping them from same height, then they must reach the ground at same time irrespective of their masses. Now for confirmation of that thing, that acceleration due to gravity is independent of mass, Galileo performed some experiment, and for this Galileo take two stones of different masses and drop them from Leaning Tower of Pisa. And if you are dropping both the stones from same height, then if acceleration due to gravity is independent of the mass, then they must reach the ground at same time. And when Galileo dropped these two stones, and he found that both the stones reached the ground at same time, so from here Galileo concluded that acceleration due to gravity is independent of mass. And he also concluded that if you remove the air completely, then a paper and a stone will also reach the ground at same time. For this, Robert Boyle uh, tested his statement. He took a long glass tube, and he put one coin and one feather at this. Suppose this is glass tube, and he put a coin and a feather at this point, and he removed all the air and all the gases from the tube using a vacuum tube. Then there was no air or gas inside the tube, that means no air resistance. Then he inverted that tube like this one, and he found that both the stone, both the coin and the feather reach the other end of the tube at same time. uh, from this experiment we can conclude that acceleration due to gravity is independent of the mass of the object. Now we have to derive formula of acceleration due to gravity, that is g for earth. We can write now. Take, we have one object which is at some distance from earth, and this is earth. Its mass is m, capital M, and its value is 6 into 10 raised to power 24 kg, and mass of object is small m, and radius of earth is 6.4 into 10 raised to power 6 meter. Now I can write gravitational force between this object and earth, we can write as capital G, capital M mass of earth into small m mass of object upon r square, and this r is radius of earth. Suppose this object is at negligible distance from the surface of earth, that's why we can consider that distance between earth and the object as radius of earth. Suppose 10 meter, 20 meter, and radius of earth is 6.4 into 10 raised to power 6 meter, then we can ignore distance between surface of earth and this object. This is gravitational force between this object and this earth. Now this object will experience this much amount of force, and from Newton's second law we can write that net force on any object we can write as product of mass and acceleration. F can be written as, if I want to find acceleration of this object, so I can write net force on that object into its acceleration. This is equation 2. Left hand of equation 1 and equation 2 is equal, then we can write both right hand side of both the equations will also be equal. So from 1 and 2 I can write m into a, this m is mass of object, g into capital M into small m upon r square. Small m to small m cancel out, so we can write acceleration of that object is g times m upon r square. This is acceleration of that object, because of gravitational force of earth, and that acceleration we call acceleration due to gravity. So I can write this a as g, and g is gm upon r square. This is formula for acceleration due to gravity. And if we put the values of mass of earth and radius of earth, we will get the exact value of gravitational acceleration due to gravity. So value of capital G is 6.67 into 10 raised to power minus 11 into 6 into 10 raised to power 24 upon 6.4 into 10 raised to power 6 square. So if you solve these values, you will get G as 9.8 meter per second square. So if you are dropping any object near the surface of earth, it will undergo acceleration 9.8 meter per second square. And you can find acceleration due to gravity at any planet. If you put mass of that planet and radius of that planet, you will get acceleration due to gravity of that planet. This is not only for Earth. You can find acceleration due to gravity for any planet if you are putting values of mass and radius. And this is the value of acceleration due to gravity at surface of Earth or near the surface of Earth. Now, Earth is not a perfect sphere. It is like oblate in shape. Oblate means it is flattened at poles, and bulging at equator means this diameter of Earth will be more and this diameter of Earth will be less. Now, if we have to find the acceleration due to gravity at this point, here this is center of Earth, so this is radius for this point, and its value is very less, not very less, something less, then g is inversely proportional to r square. If value of r is less, then acceleration due to gravity will be more. So at this point means at pole, acceleration due to gravity will be more because radius is less, so acceleration due to gravity will be more. Now if we want to find the acceleration due to gravity at equator, means at this point, this radius is more, and as value of r is more, then acceleration due to gravity will be less. So at equator, acceleration due to gravity will be less. Acceleration due to gravity at equator is 9.78 meter per second square, and acceleration due to gravity at pole is 9.83 meter per second square, because radius at poles is less and radius at equator is more. Polar diameter of Earth is 12,714 kilometer, and equator diameter of Earth is 12,756 kilometer. That's why acceleration due to gravity at different points is different. Now, we will see variation of acceleration due to gravity with height and with depth. Variation in g with height. Suppose this is Earth and this is radius of Earth. We have to find acceleration due to gravity at h distance above the surface of Earth. As the distance between object and the center of Earth is increasing, as distance is increasing, as I told you earlier, that g is inversely proportional to r square, and if you increase the distance, acceleration due to gravity will decrease. So as you go above the surface of Earth, acceleration due to gravity will decrease. Now we will derive the formula for this. G equal to capital G m mass of Earth upon r square. This is formula for acceleration due to gravity at surface of Earth, and this is radius of Earth. We have to find acceleration due to gravity g. Let's say acceleration due to gravity at h distance above the surface of Earth is g dash, and distance between center of Earth and the object will be r plus h. Now write the formula. G dash equals to capital G. Mass of Earth will remain the same, m upon r plus h whole square. This is the new distance between the object and the center of Earth. Now suppose I am multiplying and dividing with r square on denominator and numerator. This will not make any difference in this equation, because r square upon r square is 1, and if you multiply any number with 1, the number will remain same. Now take this r square this side and this r plus h whole square this side. So I can write g m upon r square here into r square upon r plus h whole square. So I can write this as r upon r plus h whole square, and this term is, what is this term? This is acceleration due to gravity, acceleration due to gravity at surface of earth, and that will be represented by g. So g prime can be written as g into r upon r plus h whole square. This g prime is acceleration due to gravity at some altitude h from the surface of earth, and as you see, if you increase the h, denominator is increasing. As denominator is increasing, this g prime will decrease. So as you go above the surface of earth, acceleration due to gravity decrease. There will be some distance at which acceleration due to gravity will be zero, because uh, as you go above the surface of earth, its value is decreasing. So there will be at some point, at that point g prime will be zero, and at that point there will be no atmosphere, because this acceleration due to gravity, this gravitational force holds the atmosphere above the earth, and when this gravitational force becomes zero, there will be no atmosphere. So we will see, remember this formula, this is important. Now we will see acceleration due to gravity, variation in acceleration due to gravity with depth. Variation in g with depth. Suppose this is earth, and if you go d distance, you are at this point, uh, d distance, d depth below the surface of earth, then this g equal to gm upon r square, this r will decrease, so acceleration due to gravity should increase, but this is not the case. As you go below the surface of earth, acceleration due to gravity will decrease. Now why acceleration due to gravity is decreasing? So this gravitational force or acceleration due to gravity is because of mass of earth attracting us towards its center. Now suppose if you are at this point, this is center, you are at this point, so mass above you will try to pull you in this direction, and mass below you will try to pull you towards the center. So say one attractive force in upward direction and one attractive force in downward direction, so net force will be something less than the force you were feeling at surface of the earth. That's why net force is less, net force is lesser, that's why g will decrease, will also less, because some part of the earth will pull you towards upside direction. Now we will derive the formula for acceleration due to gravity with depth. You are at this point. Say radius of earth is r. So this distance will be, this is r, uh, this is, say this is sphere 1, that is we are considering earth as perfect sphere for this calculation. Sphere 1, this is earth, and its mass is capital M, mass of earth, and its radius is r, and this is smaller radius. You are at this point. Then we draw a imaginary sphere at this point, sphere 2. Its mass is say m1, and its radius will be this distance minus this distance, that is r minus d. Now can we say that density of both the spheres will be equal? Why? Because this is similar object. This smaller sphere is also the part of bigger sphere. I have this paper. Density is basically number of atoms in per unit volume, or you can say amount of mass in per unit volume. So if I take that smaller part and one bigger part, I have this paper, one this part and one bigger part. So if I see mass per unit volume, mass of 1 centimeter cube volume, this will be equal, say its mass, this is 1 centimeter cube and its mass is 1 gram. So if this is the volume of whole paper is 100 centimeter cube, then mass of this whole paper will be 100 gram, because this is one paper and its atom will be arranged in similar way throughout the whole paper. So we can say its density will be equal. So I can say density d1 equal to d2. As you know, density is equal to mass upon volume. So d1 is our bigger sphere, density of bigger sphere, mass is m, mass of bigger sphere is capital M, that is mass of earth, upon volume is 4 upon 3 pi r cube. This r is radius of earth. For d2, mass of this smaller sphere is m1 and its radius is r minus d. So we can write 4 upon 3 pi r minus d whole cube. So 4 upon 3 to 4 upon 3 cancel out, pi to pi cancel out, and I can write from here m1 equal to capital M r minus d whole cube upon r cube. This I can write as m. If you take this r minus d whole cube, you can take that this term like this. So it becomes 1 minus d upon r whole cube. Now for acceleration due to gravity, I have to erase this part. For acceleration due to gravity, we have to write g m1 upon this r minus d whole square, mass of this sphere and radius of this sphere. Now m1 we can write as m 1 minus d upon r whole cube, m 1 minus d upon r whole cube upon r minus d whole square. I am erasing this part now. We can multiply and divide by r square on denominator and numerator. As I told you, this will not make any and change in the value of this term, because r square upon r square is 1. So if you multiply this r square inside this bracket, so r square minus d whole square upon r square, I can take this inside the bracket and I can write square upon this bracket. So it becomes r upon r 1 minus d upon r whole square. So I can write this term as gm 1 minus d upon r whole cube. This r I am taking here and this r will remain as it is. So r square, and it becomes 1 minus d upon r whole square. 1 upon d by r whole square. This square to this power cancel out. So we left with g m upon r square 1 minus d upon r. And this is the value of acceleration due to gravity at surface of the earth. So I can write this as g. So g prime equal to g 1 minus d upon r. As you increase the d, means you are going more below the surface of earth, then this term will increase and this term will become less. That means g prime will decrease. Case 1, you are at surface of earth. If you are at surface, then d equal to 0. This depth will be 0 if you are here. D equal to 0. So put d equal to 0, you will get g dash equal to g. Means you are getting acceleration due to gravity at surface of earth. Case 2, you are at center of earth. If you are at center of earth, this d becomes, means you are at this point, then this d becomes equal to r. D equal to r. So if you put d equal to r, this becomes g dash equal to g 1 minus r upon r. R upon r means 1. So g 1 minus 1 0. So is equal to 0, means there will be no acceleration due to gravity at the center of earth. I will explain this in more detail. This is earth. If you are at center of earth, so this part above you will try to pull you in this direction, and the part below you will try to pull you in this direction. So the net force on you will net force F1 minus F2, and these forces will be equal because these two parts will be equal. So I can write F1 minus F2, F minus F, this is 0. So net force on you is 0. That's why acceleration due to gravity will also be 0. Now we will see some numericals based on these formulas. Write these formulas for calculating acceleration due to gravity for any planet. G dash equals to g m upon r square, and variation of acceleration due to gravity with height, g prime equal to g r upon r plus h whole square, and variation in acceleration due to gravity with depth 1 minus d upon r. Now first question is, find acceleration due to gravity. Find acceleration due to gravity at center of Jupiter. You have to find acceleration due to gravity at the center of Jupiter. So G is given by G 1 minus d upon r, variation in G with depth. So if you are at center of Jupiter means d equal to r, that depth becomes equal to radius of Jupiter. If you put this d equal to r in this equation, you will get G prime equals to G 1 minus 1 means 0. So acceleration due to gravity at center of Jupiter will be 0. Now another question. Find acceleration due to gravity find acceleration due to gravity at surface of moon. At surface of moon, given mass of moon is 7.4 into 10 raised to power 22 kg. I am not sure this is the exact number, so I am just telling you the way how you can solve such questions. And radius of moon is something 1740 kilometer, and you have to convert this into meters. So 7 into 10 raised to power 3 meter cube. And you have to find G. So acceleration due to gravity is given by G into m, mass of planet, upon radius of planet whole square. So G is 6.67 universal gravitational constant, minus 11 mass of moon 7.4 into 10 raised to power 22 upon radius of moon whole square 1740 into 10 raised to power 6 3 whole square. If you solve this equation, you will get G as 1.63 meter per second square. So acceleration due to gravity at the surface of moon is 1.63 meter per second square, and acceleration due to gravity, this is moon, and acceleration due to gravity at surface of earth is given by given as 9.8 meter per second square. So if you try to find this, G at earth is 6 times G at moon. So if your weight is 120 Newton at earth surface, your weight at moon surface will be 1 upon 6 into 120, that is 20 Newton on surface of moon. Now we will take another question. Now we will take one question on variation in acceleration due to gravity with height formula, that is G dash equal to G r upon r plus h whole square, this formula. So question is, find the height of the surface of earth, the surface of earth at which acceleration due to gravity is reduced by 36%. As you go above the surface of earth, acceleration due to gravity decreases. And now in this question, it is asked that you have to find the height at which acceleration due to gravity is reduced by 36%. So we have to find what value of g will be at that point. So if g is reduced by 36%, acceleration due to gravity is reduced by 36%. So acceleration due to gravity at that point will be g dash will be, suppose at surface it is 100%, and at that height h it is reduced by 36%. So 36% of g, percent means 1 upon 100 minus 36 upon 100 into g. So this will be 64 upon 100 into g. So acceleration due to gravity at that point, at that height, will be 64% of the acceleration due to gravity at surface of Earth. Now we have to find that height. We can write g dash equal to g r upon r plus h whole square. This is given as 64 by 100 into g. Put here into g equal to g r upon r plus h whole square. This g to g cancel out, be left with 64 upon 100 equal to r upon r plus h whole square. I can write this 64 as 80 square and 100 as 10 square. So I can write 8 upon 10 whole square equal to r upon r plus h whole square. Take square root on both sides. So square to square cancel out if you are taking square root on both side. So we will left with 8 upon 10 equal to r upon r plus h. Do cross multiplication here. 8r plus 8h equal to 10r. Take this r to the right hand side. So we left with 10r minus 8r will be 2r equal to 8h. So take this 8 to the left hand side, h equal to 2r upon 8, that is 1 upon 4r. So at the height 1 upon 4 of r means 1 upon 4 I can write as 25% of radius of Earth. So height is, at the height 25% of radius of Earth, the value of g will reduced by 36%. We will take few more questions. And a planet has mass twice the mass of Earth and its radius is twice the radius of Earth. Find acceleration due to gravity at surface of this planet. Face of this planet. Mass of that planet is 2 into mass of Earth. This is given part. And radius of that planet is twice of radius of Earth, and we have to find acceleration due to gravity at surface of that planet. So acceleration due to gravity is given by g into mass of planet upon radius of planet. So put the value of mp. G mp is equal to 2 into me. Mass of planet is twice the mass of Earth, so I can write this as 2 into mass of Earth on radius of planet. I can write as 2 into radius of Earth. 2 into radius of Earth whole square. So on solving this, g into 2 into m e upon, this becomes 4 into radius of Earth whole square. This I can write as 2 upon 4 into g into mass of Earth upon radius of Earth whole square. The value of this term is g into mass of Earth upon radius of Earth whole square. This is acceleration due to gravity at surface of Earth, and this is given by 9.8 this meter per second square. So this is 1 upon 2 into 9.8, it becomes 4.9 meter per second square. So acceleration due to gravity at the surface of that planet will be 4.9 meter per second square. Now take this question. The value of g at surface of a planet is 12 meter per second square. If radius of that planet is 2.58 into 10 raised to power 3 kilometer, find its mass. G is given. This is 12 meter per second square. First write given part. G is given and radius is given 2.58. If we convert this into meters, I can write this is 10 raised to power 6 meter, because 1 kilometer equals to 10 raised to power 3 meters. So this is 2.58 into 10 raised to power 6 meter, and we have to find mass. I can write G equal to G m upon r square. From here, if I have to find mass, I can write this as G on G into r square upon capital G. So put the values. G is 12 into r square means 2.58 into 2.58 into 10 raised to power 6 into 10 raised to power 6 upon value of capital G is 6.67 into 10 raised to power minus 11. 2.58 into 2.58 becomes 6.67. So 2 point, this cancel out and we left with 12 into, this is 10. I can write a power m into a power n as a power m plus n, and a power 1 upon a power minus m can be written as a power plus m. So I can write this as 10 raised to power 6 plus 10 6. This becomes also plus 11, because when it I take this in numerator, it becomes positive. So this is 12 into 10 raised to power 6, 23. 12 and 11, 23. So mass of that planet is 12 into 10 power 23 kg. These are very easy questions. Just you have to put the values in formulas, nothing else. Now we will take one more question. If radius of Earth, if radius of Earth shrinks by 25% and mass remains the same, mass remains same, find acceleration due to gravity. Find acceleration due to gravity. Find acceleration due to gravity. So radius is shrinks by 25% means radius becomes shrinks means it is 25% less than the previous radius. So I can write r dash equals to, suppose in previous case radius was 100%, 100% of radius of Earth. Now it becomes, it is shrinks by 25% means 25% radius we can subtract. So this is 100 upon 100 means r minus 25 upon 100 r, it becomes 75 upon 100 r. I can write this as 3 by 4 r, and if you put the values, g equals to g m upon r dash whole square, because mass is same as this was in previous case, so only radius changes. So g m upon 3 by 4 r square, g m upon 9 by 16 r square. You can write this 16 in numerator, so it becomes 16 upon 9 g m upon r square. What is this term? This is acceleration due to gravity at surface of earth, and its value is 9.8. So it becomes 16 upon 9 into 9.8, and it becomes 17.42 meter per second square. That's it.